very distinguished panel today. I'll just do a very brief introduction to everyone, just in the context of this panel. So the panel consists of Scott Aaronson, who we don't need to introduce here, but I'll just say that his article on reading the fine print is sort of what we want from him in the panel to keep everybody honest in terms of machine learning. Andras Gilyén, you already heard, is one of the principal authors of this quantum singular value transform that Gilyén talked about today. Ravi Kannan is our representative of he's one of the great algorithmists in classical linear algebra. So he represents that side of the equation. Iordanis Kerenidis is he's been working very intensively in quantum machine learning. In particular, he's the head of quantum algorithms at QC-Ware. He was part of this Kerenidis Prakash recommendation algorithms, the quantum algorithm for recommendation systems. And Patrick Rebentrost from CQT, has worked extensively on quantum machine learning and actually including quantum finance. He was on the very influential 2017 Nature paper on quantum machine learning. So without further ado, I'll just open up the floor to the panelists to give a 2 to 3 minute commentary on their reaction to Ian's talk or to quantum machine learning in general, and we'll proceed from there. So Scott, maybe.
Well, all right. I appreciated the talk. It's always good to hear from Ewan. I mean, even though my role in this in Ewan's story was mostly just giving Ewan this problem to work on, but I'm proud of that role. I kept thinking, since she mentioned this 2014 survey article I wrote called Read the Fine Print, I kept thinking about, like, if I were to write it again today or update it, like, would anything be different, right? Like, what has changed in the outlook for quantum machine learning over the last 7 years or so? And and it looked like there would really be two main things, right? One is just this sequence of dequantizations that that's started with Ewan's work, that I sort of warned abstractly in that 2014 article that such a thing could happen, but I think people didn't take it as seriously until it actually did happen. So it's funny that way, right? And I think Ewan had this nice graphic of, I guess, the growing purple, was it, or the growing like almost like Mordor or something, or like some dark wizard taking over the quantum machine learning algorithms, dequantizing one after the next. And so I think just like in 2014, I would say, like when I talk to business people or to journalists, or I give colloquia and people ask me about how is quantum computing going to revolutionize machine learning, the answer I give them is, well, eventually there should be Grover type speedups. And as for whether there are exponential speedups for any machine learning problem that people care about in practice and that would survive, dequantization, Ewanization, whatever you call it, I don't know, right? I think the jury is still out on that. I think we lack any example that is nearly as compelling as, let's say, factoring or quantum simulation for quantum algorithms more broadly. And I think, that's the answer I would have given in 2014, and that's still the answer that I would give today, despite all that's happened. Now, the other thing that I would change is that so much of this has been can now be sort of rephrased in this much more general language of block encodings, right? So it might be that the upshot is the same, but we now have this sort of more powerful language for talking about everything, both the quantum upper bounds and the dequantizations of them. And I think that's something that came through clearly in Ewan's talk. So anyway, I'm happy to hear. This is not, I would say, the area that I'm expert in, and I'm happy to hear other people's thoughts.
Great. I had a question for you, but I'll wait for the rest of the panel. Andres?
Yeah, I think that, yeah, indeed, Ewan's talk was really nice in like putting together, like summarizing this language, the block encodings, and then how you can actually dequantize it and draw a direct parallel. I think it's very nice that like these techniques developed by and all these improvements in quantum machine learning came from quantum physics, like this linear combination of unitaries first appeared in a paper in Andrew Childs and Nathan Weeb, and then this like qubitization, quantum walks, all these tricks by Ike Shuang, Guanghao Lo, and Mario Segre, all these things came together. So it's wonderful to see how quantum machine learning benefits from all these ideas which originate from deeply in quantum physics. But this connection also was discovered, and for that reason, I think just as we don't expect that simulating sparse Hamiltonians will be ever feasible on a classical computer, and it's a close connection to some matrix inversion problems and so on, I don't expect that in the sparse matrix regime you will be able to dequantize these algorithms. So there, I really expect that just like Hamiltonian simulation, we will see a genuine quantum speedup. However, it's very hard to exploit that speedup, as Scott pointed out in his paper. So we definitely need more work on that. And some very interesting recent results that even also touched, for example, this optimized random features paper where the author showed how to speed up a sampling task for something which is actually practical in a learning algorithm and gives somehow the optimal distribution to sample from. This is actually seems to be a very, very useful thing in this machine learning setting, and due to its connection to sampling and some other nice representations of the matrices, this might be a very interesting candidate for getting speedups. Also because the first supremacy claims also show that quantum computers have an edge in sampling from some funny distributions. While those distributions may not be immediately interesting for some practical tasks, but these authors found a problem which actually seems to be relevant for machine learning. And deep inside, it also has some Fourier transform involved. Somehow, the matrices that it uses to construct its like core subroutine is somehow, if I understand correctly, it's a composition of matrices which are either sparse in the original basis or in the Fourier basis. And like you can be efficient or diagonal or something, and maybe you could efficiently work with either of those matrices individually in a classical setting. But once you put a linear combination of those, which is either nice in the computational basis or either nice in the Fourier basis, once you have to work in both bases at the same time, then classical algorithms have a hard time, and we don't know how to dequantize that. And I expect that such kind of settings will actually defy dequantization. So I'm really interested about these recent developments, and I hope that we will see genuine exponential speedups eventually.
Great. Thanks, Ravi.
So yeah, thanks for the very nice talk. I'm not so familiar with quantum computing, but as Umesh introduced me, I'm from the classical area. I was thinking what I could do usefully was perhaps tell you of at least one problem in which quantum and classical may or may not make a difference, and we don't know the answer. At least I don't know the answer. Some of you might have considered this problem. This is the tensor analog of singular value finding. So the top singular value of a matrix A is just the best X transpose AY you can get over unit vectors X and Y. Now, if you had a 3 tensor, this applies to any R tensors, but let's say you have a 3-dimensional array, AIJK, then you can ask for the unit vectors X, Y, Z, which maximize sum of AIJK, XI, YJ, ZK. Okay? And I think this is NP hard, probably, at least if you go from 3 to 4 or 5, it's NP hard. But it is known, there's an approximation algorithm known, which for any tensor comes within an additive factor of epsilon times the Frobenius norm. Very similar to our approximation algorithm for matrices. This was in a paper in 2005, Stock or something. Now, all the linear algebra, nice machinery that you have goes out of the window now. But the sampling oracle, the length squared sampling oracle, is again something we use centrally for this algorithm as well as the other. So for that reason, let me throw out this question. And again, I'm not familiar with the recent literature, and some of you may know the answer or may work out the answer in the next few minutes. But let's throw out the question, is there a quantum advantage to this? Can you do better in terms of error or the dependence on R when you have an R tensor? The dependence is exponential in R at the moment for R tensors as R grows, but polynomial time in the other parameters. So if you have ready-made answers, let me know. Otherwise, by the end of this talk, you can tell me the answer.
Okay, so we'll circle back to that by the end of the panel. So Iordanis, would you like to go next?
Sure. So yeah, first of all, thanks everyone for the talk. It's always very nice to hear your talk and how you explain things, and how you can see that the work has evolved, and now you're talking about these very general kind of frameworks that make a lot of sense, and it's something very interesting even beyond machine learning, right? So I think Umesh kind of posed us a question, offline, or to try to answer in these 2-3 minutes, which is there a potential for quantum advantage in machine learning, in quantum machine learning, right? So I'm going to try to figure out how to answer this question in 2 minutes, let's say. So I guess I'm going to take maybe the easy way out and say that the only reply I can give is that we have to keep trying, right? So I cannot say that there will be, but I also think that, I don't want to take the easy way out and say that there's not going to be. So I think the best thing we can do is keep trying. And there are a few reasons that I want to give you why we should keep trying, right? So first of all, okay, machine learning is important. It's pretty everywhere. So I guess if we manage to get any enhancement with quantum, that's good, right? And it's not like we have a million opportunities to find, applications and fields where quantum can very easily provide advantages. So anywhere we can try and get an advantage, I'm happy to keep working on these things. And I guess the second reason is basically what Erin said in her talk, that we have some very powerful quantum techniques, right, which are useful for machine learning. All the singular value transformation techniques and different other techniques that will keep coming up. Techniques on loading data or estimating distances, or some even newer techniques on how to do volume sampling, and all of these things. At least we have a very good starting point, right? We have a theory that says there are some very strong, powerful quantum tools that we can start using, right? It's not the end of the story. We don't go from there directly to I have solved all my machine learning problems, but I think it's a good starting point. And it's also very subtle, right? These powerful tools, we saw they're very subtle, and we have to be very careful and read the fine print. I totally agree with everything that Scott said 5 years ago, or he will repeat today. But I also want us to read the fine print on both sides, in the sense that what do we mean, that we don't have a speedup? We mean that there is no provable exponential speedup, right? And right now we start from a position that we have for some problems, large polynomial speedups. Okay, so it would be much better if everything was an exponential speedup. I totally agree with you. I will take a speedup which is an order of 8 difference between linear and n to the 8. Again, I'm happy to work on this and try to see if in practice we can actually get, you know, a speedup. And if we want to go even more precise on the fine print, I don't think that the real practical running time of this quantum-inspired algorithm is this n to the 22, 12, and all this. I think they're better than that, right? I think we all think they're better than that. At the same time, you know, I've talked with Ravi many times. I've talked to the randomized linear algebra people. The question is, are these quantum-inspired algorithms right now better or worse than the more traditional classical linear algebra techniques that people use, right? And for now, they are not faster, okay? Which means that if my goal is to provide a speedup with the best possible classical practical algorithm, I still have, you know, the CUR type of algorithms, for example, for doing recommendation systems, which depend on the dimension. So you can see it both ways, and I'm trying to, you know, to say that either what I really want to say, and this is machine learning, it's not an exact science, it's not TCS. I want to see if there is a potential to give a quantum advantage in practice for some machine learning application, right? And you can either think of it as an exponential or a large polynomial gap. The question is what will be, you know, best at the end when we'll try to implement this. So I agree with Scott that if we end up only having to deal with Grover, maybe that's not going to take us very far, right? But we do have much bigger polynomial gaps and much stronger techniques than just Grover, right? You can do all this spectral analysis type of stuff, right? You can do fast things, you know, phase estimation, singular value estimation, all of these things. I think we should keep working to find the good applications. And just to, you know, one last thing is that to me, what I've been trying to do, you know, I kind of, you know, all of this quantum inspired thing is great. And it started with these recommendation systems. If I knew that it would make such a havoc, I wouldn't have said it's an exponential gap. I would say it's a big gap. So then we wouldn't have to do all this. I still think it's a very interesting gap, whether it is exponential and polynomial. And what I've been trying to do this last 4 or 5 years is figure out really how close can we bring these algorithms to something that we can see in reality, right? We don't start from the easiest, you know, point. We need to load the data. We need to have this block encoding. We need to do many things. But I don't see a fundamental reason why I would say that there is no way we can get a speedup. So as long as there is no fundamental reason why there shouldn't be a speedup, I'm happy to continue to work and on quantum machine learning. And we are more and more getting closer to getting all these linear algebra techniques, for example, not, as Erwin had an open question at the end, not through this QSVT framework, but much nicer ways of doing the same thing with much shallower quantum circuits that implies that they're also more noise resilient and so forth. So I stop here.
Okay, great. Thanks, Iordanis. Patrick,
Can I ask a question related to that, or I guess it's in the middle of the panel? So you're saying that that when you look at the classical version, this dequantized, and you compare it to other classical, well-studied algorithms, there is no advantage, and actually there's a disadvantage. But I guess comparing running time is not the only thing, and I'm wondering if there are some applications or architectures where there's some native operations, which are the same native operations that are using in the dequantized version. I'm thinking specifically about encryption-inspired stuff, where something polynomial operations are much easier than other non-kind of linear operations, that it could have an advantage in such a setting. So it's not. So all I want to say is that I would not look at running time as the ultimate test. I would look at sort of what is a natural operation maybe in another setting. And if these algorithms give you a completely different type of sort of algorithms, maybe they don't, but maybe they do. I don't know. It's the first time I've seen this. Yep. Then that could be interesting.
Okay. Yeah. Can I comment? So yeah, so if you look at the setting where quantum inspired algorithms work, it's actually like a very, very weak, like the set of assumptions are very, very, very weak. Like it's weaker than like a streaming assumption. It's weaker than like a sparsity assumption. It's weaker than like the standard randomized numerical linear algebra assumptions. But the other thing is that it's a little bit of a strange assumption, like to have, for example, sample and query access to your input. It's a little bit, I'm not aware of applications in, for example, just like TCS generally, where such an application would be useful. But I think like I would definitely be interested to hear if such things existed. But yeah, that's basically like my understanding for why like these algorithms, I guess, are new in some sense, and they're the fastest in like that particular model. But compared, like, you know, actual computers, if for actual computers, you know, things like iterating over all the entries are like, you know, reasonable, and so for these reasons, these algorithms don't necessarily, they don't perform as well as like standard things like count sketch or whatever. And yeah, I guess like I'm not entirely sure how practically, like how practical even these numerical linear algebra sketches are. I guess I'm not that sure, but I'm not aware of very many cases where it's actually used in practice. But yeah. Great.
Okay. So let's just continue with the last panelist, who Patrick, who is I think it's very late for you, so thanks for joining us from Singapore, and looking forward to hearing what you have to say.
Yeah, so I mean, first of all, great talk, Ewan, awesome. It's great to see all this coming together, and also, you know, advancing the quantum side, the classical side, and see what kind of speedups survive and so on. I think that's great. I don't have any great talk or any short speech prepared. I mean, something like what you showed on the HHL slide, I think that makes that looks actually quite optimistic. I mean, quite good, right? There's still a large polynomial gap, as also Iordanis mentioned. So that sounds, at least sounds quite good for now. I believe that the classical algorithms can be improved, and as you also mentioned, I mean, for example, Ashley Montanaro's recent paper using the Kaczmark's method seems to be improving some of these these exponents. So so right now, for example, I'm working a lot on just polynomial speedups, just using standard methods like amplitude amplification and amplitude estimation to get small polynomial speedups. And often we look at sort of a classical algorithm for a learning problem, and we find the lines in the code that we can replace by quantum subroutines, and then try to figure out what is the overall speedup. And often we get again a quadratic speedup in some variable, and sometimes even a slowdown in other variables. So we have, for example, looked at the learning of Ising models, so the graph of an Ising model, the provable learning. So these are just things that I'm looking at, and I mean, I'm happy to answer any other question, any specific questions.
Great. Thanks, Patrick. So before we go on, I want to channel a virtual panel member who is our speaker from the last colloquium, Matthias Troyer. So Matthias in his talk spoke about how anything that's a quadratic speedup or a subquadratic speedup is just not going to have any, it's not going to provide us a speedup for, not just the near future, but the foreseeable future, because quantum computers, the cycle time is just going to be so much slower that you would have to go to instance sizes that are so large that it's really not going to be practical. So maybe Scott or Iordanis, how would you react to that? To what Matthias had to say?
I think that's probably true. I mean, I was kind of on the fence about whether Grover speedups would actually matter in practice in the near future. And these calculations, I think, have made it clear that, if they will, then it's going to be not for quite a long time, right? Not for quite a while. And so when one really wants larger, ideally exponential speedups. But one thing I was thinking about while I listened to Iordanis's comments is, what examples do we have in all of quantum computing of speedups that are more than quadratic and less than exponential, right? I can think of only very, very few in the entire field. There was some, Wim van Dam, right, had something for some number theory problem that I think was a cubic speedup. Okay, the dihedral hidden subgroup problem. That's sure. That's a black box problem, but you go from 2 to the n to 2 to the square root of n. Thank you, Ike.
The linear algebra ones, Scott.
What?
Right? The n-cube linear algebra problems from classical, right? So the idea is to go from the n-cube things like PCA or volume sampling, all of these kind of hard linear algebra questions where you do need this cubic kind of or almost cubic dependence to get them into linear quantum time, right? And we have some examples of that. So this is kind of a bigger gap, let's say, than a Grover, and it's not based on Grover that you have to do the queries and things like that. There are not many. They're the same. There are not many. Anyways, even exponential, we don't have many, right? I mean, yeah. But what Matthias says, okay, if things do not improve, then we're not going to see anything in practice, right? If the hardware doesn't become faster, if the algorithms don't become better, as in needing fewer qubits or less time, we're not going to see it, right? If everything stays the same, we're not going to see it. I don't see any. I think, though, it's a very pessimistic way of thinking, right? Because if you would ask the same question 3 years ago or before or in 3 years, our knowledge changes, right? So sometimes it changes for the negative, meaning that we get lower bounds and we say, okay, we were trying, but we're not going to get it. But most of the times we get new algorithms. Like the biggest.
Well, not right. Well, none of this was an argument for not looking. Certainly, right. We're in total agreement about that. But I mean, finding new algorithms cuts both ways, because it's finding new quantum algorithms, also finding new classical ones, right?
Sure. Yeah. My goal is to find new algorithms, let's say, right?
Yeah.
Great. So, Ian, you had maybe, do you want to respond to all these comments?
I don't really have much to say. I also think it's like, I think what like this stuff, these like that more than Grover is probably necessary is it seems reasonable, and that's, I think, why like yeah, I think that's interesting, because it does cut down a lot on like the number of possible machine learning applications if you like ones that seem actually feasible to implement in the short term. Yeah, I don't have very many thoughts.
Okay, great. I had a quick question, actually turning to Patrick. In terms of this other approach, some sort of a variational approach to quantum machine learning, where where one starts with a number of qubits which is modest, 50, 100, 200, but which is very hard to simulate classically. And then one says, look, variationally we are training something and maybe it does something. So it's something that we can't do classically. So what would you say to that type of approach? And what are the possibilities there? And how optimistic should we be about that?
I think for applications like in chemistry, I think we can be quite optimistic, I would say. I mean, the variational approach has been used in chemistry on classical computers. So I think in general, I would believe that chemistry would be, if at all, the first application of these methods. Machine learning maybe after, but I believe that chemistry, because I mean the chemical problem itself is a quantum mechanical problem, and so it will probably be easier for near-term quantum computers to provide some sort of insight into these chemical problems. So yeah.
Great.
I mean,
by the way, I should have mentioned before, but there's a whole world of machine learning problems that are for quantum problems, right? That you know, are about learning a quantum state, and where, you know, there is no barrier at all, it seems, to getting exponential quantum speedups. But you know, I took it that wasn't what we were talking about.
Yeah, but while you're at it, Scott, is it, you know, is there a particularly striking you know, example of such a quantum machine learning, you know, with quantum states problem?
Right. Well, there again, I would say, you know, it's not obvious what the examples are. I mean, you know, there are you can imagine machine learning tasks where quantum simulation would be a subroutine in them, right? Like maybe, you know, learning the behavior of a protein, for example, you know, based on various data, right? And you know, that might be, you know, that in the end that it's heuristic and there's not really a rigorous analysis, but for the quantum simulation part in the middle, you know, for that we believe that there's an exponential speed up. But yeah, it would be great to have something better even there.
Right.
Yeah, if I may add, like one of the problems with quantum machine learning, it's just hard to input this large data into the small quantum computers that we have. So if we start with some quantum mechanical model and like generate the quantum data on the fly, then we don't have the problem of like having to measure the quantum state on the first place. And we also solve the problem of the input of the quantum machine learning algorithm. So like one of the examples that like people say that maybe quantum simulation will be useful for understanding some catalysts like nitrogenase. But it's also a bit unclear to me how would a quantum simulation help in understanding that molecule? How would they use the output of the simulation? Maybe the ultimate approach which will win, that somehow you simulate the molecule and you use quantum machine learning to understand the structure, which is like the underlying key features that makes your understanding whatever need to be. And there, like the input is small and the output is small, and in between the large input-output like intensive part, which is the problem in quantum machine learning, is solved by this like keeping everything quantum mechanical. I think that is one of the key messages in this block encoding, that don't convert your data back to classical, just keep it always quantum, and that seems to help a lot.
So one other case is when you have to pre-process your data with something linear algebraic, like do a PCA or project it into some subspace or do a kernel. So there, the bottleneck is not the dimension of your data, but it's the fact that you have to do this cubic operation on it, right? So there, even if your quantum uploading of data takes linear time, you're still getting, if the mapping, the PCA, for example, or the kernel can be done fast, then you end up with a quantum state as you need it in a computation which is much faster than the cubic thing that you would need to do classically. So this is also another case where you can do the pre-processing quantumly. This is what we did in the recommendation systems as well, right? You project your user in the top subspace, and then you keep it as a quantum state, right? This is the thing that is difficult, and that's why you're getting these 6, 8, 12 powers. So it's not just loading the data, right?
Great. Like Ike Chuang has a question. Ike?
Yeah, inspired by what you've been asking, Umesh, and your answers, those of you on the panel, it occurred to me the following, because, you know, when I was a postdoc with Umesh, you instilled in me this firm belief that quantum will have no advantage if there's no structure to the problem. and that the only case where you expect an advantage is if there is some kind of structure, because that structure may match the nature of quantum mechanics underlying it. And if you ask a physicist, an experimentalist, almost no experimentalists except those who are motivated by other concerns, let's say, believe in QRAM. And I certainly don't believe in QRAM and have never believed that we would ever be able to physically realize a QRAM. Now, on the other hand, Scott and folks have been raising, Patrick and company, that the point that chemistry is very appealing and machine learning questions in chemistry. But if you're an experimental physicist and you ask yourself, where's the structure of hard quantum questions? It's not in pure quantum systems, it's in noisy quantum systems. So my question to you in the panel is, how would we think about block encoding noisy quantum processes, where the quantum process is not just a unitary or a Hermitian or a Hamiltonian, but rather something that has classical noise, classical stochastic, as well as Scott yawning at me at the same time, because it should really be hard, quantum and classical. What do you think? Sorry, Scott. I think you owe yourself the first answer since you found this.
Me? I don't know. I mean, you know, we know ways to deal with noise. I mean, you know, I mean, often you can do it by just passing to a larger, you know, Hilbert space and just tracing part of it out. You know, now there is work like my former postdoc Chun-Hao Wang and then Richard Cleve, you know, did some work on in what cases can you do better than that? Like if you have Lindblad evolution, you know, and you want to simulate it, you know, when can you do better than passing to a larger Hilbert space? But at the very least, you can always do that.
But I want something more efficient, because I suspect that distinguishing two distributions, which are noisy quantum distributions, classical noise added to quantum, is probably a great model for the hardest machine learning problems. And those which you might expect a quantum advantage for.
I don't know. I mean, you know, often when people say, "Oh, you know, the presence of noise just you know enhances things for us," or it means that, you know, we're more likely to get a quantum speed up. You know, in the past, that has often been a red flag for me, right? It's you know, like the history of claims of that kind, I think, has not been a strong one, because, you know, the intuition is, as you would expect, as you add more noise to something, it becomes easier to simulate classically. You know, and if there are examples going against that, I'd be very interested to see them.
There is a great example, which is the one from IBM with Smolin, Graham Smith, and Andrew Cross, right? What was it, parity checking with noise, and in that case, it is a simple kind of machine learning problem, and they find that there's an exponential advantage for the quantum algorithm over the classical as the noise increases, largely because the quantum algorithm was immune to the noise, so the noise was structured in a particular quantum way. But I submit to you that what we're missing is a classical framework to be able to handle these cases where the noise is structured in a quantum mechanical way. I don't know.
Okay, yes, I'm not sure what you mean by the noise being structured. If you want to send me a link to that paper, which I don't know, I'd be happy to take a look at it.
Will do.
Just one quick thing for Ewan before, you know, so soon we are getting towards the end of the panel. I put a GatherTown link on the chat for anyone who wants to join afterwards. But Ewan, just very quickly, you know, in your chart that you showed, you know, as things moved, you know, from potential exponential advantage and, you know, towards more and more likely not in that graph, there were a few things that still stood out in the potential exponential advantage. Can can you say a little bit about what you see as the most promising ones of those, and just maybe a couple of sentence description of those particular problems?
Yeah. So I guess the ones that I thought were the most interesting, I discussed already. So the ones that were the most yellow were the Gaussian process regression, which I discussed. It's an interesting. I don't really know what Gaussian process regression is. I think it has something to do with basically it's like some sort of regression, and it involves like a Gaussian kernel. But I think this has been like floating around for a while, and I guess it uses some, I think, heuristic arguments to say that like that you could sparsify the matrices that you want to invert and then use a like HHL. And the same basically holds true for the topological data analysis. There you're assuming that it's sparse, and then using it to, I guess you want to estimate the dimension of the kernel of like a combinatorial Laplacian, and this is a little bit strange to do such a thing, because the way that you estimate it is you estimate you don't estimate like you don't get an approximation of the dimension exactly. You approximate all of the singular values, and then you just truncate and like assume that everything that's sufficiently small is zero. And so you don't actually get a real approximation algorithm in the sense of like a ratio or something. I think there's been recent work sort of talking about possible reasons why this might give some speedups. There was a paper recently that sort of says that a generalization can be used to simulate the one clean qubit model. It's getting a little far from my area of expertise. But I also agree with Andras that like this example with learning optimized random features is very interesting. One of the downsides is that it does use QRAM. I guess like they all use QRAM, and that makes me somewhat skeptical of like any of these applications, to be honest. So it's not clear to me how like my job is not usually to like think about like, okay, what's like the most practical machine learning algorithm, and so I don't usually need to think about these concerns, but I'm not actually sure about like whether I would consider these like I would definitely consider all of the ones that were on my slide to be far from practical, in a lot of senses. I mean, but probably like primarily the fact that they use QRAM, and yeah, I guess it's just something I would like definitely consider like maybe more interesting on the practical side would be something like I think like Aram Harrow gave a talk recently that was about like quadratic speedups, but that didn't have like such large assumptions like QRAM and things like this. And I thought those like I agree that like quadratic speedups are also maybe not that viable for like quantum speedups in the short term, but I think they're also like maybe they're more viable than like a QRAM based system. I'm not sure. Yeah. Did I answer the question?
Yeah, no, that was good, and you even proposed a hierarchy of what what might be more or less viable, which is interesting. Yeah, no, that's great. So I think we should we are really this was a great discussion. We can continue this on GatherTown if anybody wants to join. And I just want to wrap up by thanking the panel for all their comments, and of course, thank you, Ewan, for always for this for a great talk. And see you all next week.
Yeah, I apologize. I have to teach. I can't make the GatherTown, but thank you for inviting me, and thank you, Ewan.
Thanks, everyone.
Thank you.
Bye.
Bye. See you all.